This is a place where curiosity and calm sit together quietly, like two old friends resting on the same stone wall, watching the sun move slowly across the sky. Tonight, we invite you to set everything down. Whatever you were carrying through the day, let it rest now gently, the way a leaf finally settles onto still water. Take a slow breath in, and let it out even more slowly. Welcome to quiet knowledge. Tonight's journey takes us somewhere ancient, somewhere vast and patient, somewhere that has been quietly waiting for billions of years, completely unhurried, completely untroubled by the rush of modern life. Tonight, we explore the most relaxing and fascinating facts about geology, the science of the Earth itself, the study of stone and time, the quiet language of mountains and rivers, of crystals forming in darkness, of ancient seas turned to rock. Geology is, in many ways, the science of patience. It speaks in millions of years the way we speak in minutes. It measures change in the slow drift of continents rather than the quick turning of calendar pages. It reminds us, gently and without urgency, that the Earth has always been here, working slowly, breathing deeply, shaping itself with the quiet confidence of something that knows it has all the time in the world. So allow yourself to drift now, wherever you are. Perhaps you are lying down. Perhaps your eyes are growing heavy. Perhaps you are somewhere soft and warm with the sounds of the night just beginning to gather at the edges of your awareness. Close your eyes if you'd like. Let your breathing slow. And imagine together with us that you are floating gently above the surface of the Earth, high enough to see the mountains as gentle wrinkles on a vast and quiet landscape, high enough to watch rivers glittering like threads of silver far below. From up here, the planet looks ancient and peaceful. It is ancient, and tonight we are going to learn why. Let us begin. Somewhere beneath your feet right now, deep below the soil, below the roots of trees, below the layers of clay and gravel and ancient compressed earth, there is rock. Not just any rock, ancient rock. Rock that was here long before you, long before this country, long before the first human ever stood upright and looked at the horizon. Rock that may have been forming, quietly and without interruption, for hundreds of millions of years. We tend to think of rocks as static things, hard, unchanging, simply there. But geologists understand something beautiful and deeply relaxing about rock. It is always in the middle of a very, very long journey. Every rock you have ever held in your hand, every stone that lines a riverbed, every cliff face you have ever stood before and felt small beside. Each one of them is a traveler through time, slowly moving through a cycle so vast and so unhurried that it makes human civilization feel like the briefest of flickers. This slow and majestic journey is called the rock cycle, and unlike the frantic cycles of modern life, the rock cycle has no deadlines, no hurry, no sense of urgency whatsoever. It simply continues, turning and transforming, taking whatever time it needs. And it always, always has enough time. Geologists divide the rocks of the Earth into three great families, each one born through a different process, each one a testament to some particular kind of patience. The first family is the igneous rocks. And their name tells their story immediately, for it comes from the Latin word for fire. Igneous rocks are born deep in the heat of the Earth, where temperatures are so immense that solid rock melts into something fluid and glowing, a substance we call magma. Imagine for a moment that you are somewhere deep within the Earth's crust. Not dangerously so, just imagine drifting, peacefully and weightlessly, through a vast underground world. Down here, far from the surface and all its weather and wind and activity, there are places where the rock itself has become warm enough to flow, slowly, incredibly slowly, like honey that has been sitting by a warm fire for a very, very long time. This molten rock, this magma, moves through the crust in gradual, unhurried ways. Sometimes it rises upward, finding small cracks and passages through the solid stone around it, pressing forward with a patience that is almost meditative. It may take thousands of years for magma to travel a distance that a person could walk in an afternoon. And then, eventually, it cools. Slowly or quickly, depending on where it ends up. If the magma reaches the surface through a volcanic eruption, which is one of those rare moments when the Earth's inner world briefly and dramatically meets its outer world, it flows out as lava and begins to cool in the open air. Lava that cools quickly, exposed to the wind and rain, forms rocks with very fine, smooth textures. Basalt is the most common of these. Dark, dense, quietly, beautiful. Much of the ocean floor is made of basalt. But if the magma never reaches the surface, if instead it simply slows and stops deep underground, cooling over hundreds of thousands or even millions of years, it forms something different, something crystalline and coarse-grained. The most familiar of these deep cooling igneous rocks is granite. Granite is everywhere. It forms the cores of ancient mountain ranges. It lies beneath vast stretches of continent. It appears in kitchen countertops and garden walls, in the polished floors of buildings, and in the boulders that rest in mountain meadows. And every single grain of it, every tiny glittering crystal of quartz or feldspar or mica, was once part of something molten and glowing, deep within the earth. Take a moment, if you can, to imagine holding a piece of granite. Feel its cool, smooth weight in your palm. Look closely at the tiny crystals embedded in it. The pale ones, the pink ones, the dark flecks that catch the light. Each crystal grew slowly in the cooling magma, taking its time, finding its geometry with crystalline precision over thousands of years. That is patience made visible. That is geological time you can hold in your hand. The second family of rocks is perhaps the most quietly astonishing of all. Sedimentary rocks. Sedimentary rocks are made not from fire, but from time and pressure. They are formed from the slow accumulation of particles, tiny grains of sand, fragments of shell, flakes of clay, the microscopic remains of ancient organisms that settle, layer by layer, over immense periods of time and are gradually compressed into something solid. Think of the bottom of a very old lake, or the floor of a shallow ancient sea. Particles drift down through the water, settling with extraordinary gentleness, layer upon layer upon layer. Each layer represents a moment in time, a season, a century, 1,000 years. The layers pile up, almost imperceptibly slowly, and over millions of years, the weight of all those layers pressing down transforms the soft sediment at the bottom into solid rock. Sandstone, limestone, shale, mudstone, chalk. These are all sedimentary rocks, and they are all, in their quiet way, record books. They hold within their layers the story of the environments that created them, the chemistry of ancient seas, the fossils of creatures that swam or crawled or drifted through worlds that no longer exist, the footprints of animals that walked across mudflats hundreds of millions of years ago. The Grand Canyon, that great and awe-inspiring chasm in the American Southwest, is essentially a library of sedimentary rock. 2 billion years of Earth history exposed in its walls, layer upon layer of stone telling a story of shallow seas and desert dunes and river deltas that came and went over unimaginable stretches of time. To stand at the rim of the Grand Canyon and look down is to stand in the present and look into the deep, past with nothing but open air between you and 2 billion years of geology. And all of it happened quietly. No rushing, no urgency. Just the slow settling of particles, the patient accumulation of time. The third family of rocks completes the cycle in a way that feels almost like a story of transformation and resilience. These are the metamorphic rocks. Metamorphic rocks begin as something else. Igneous rocks, sedimentary rocks, or even other metamorphic rocks. But over time, as the crust shifts and moves and thickens, these rocks find themselves buried deeper, subjected to great heat and immense pressure. Not enough heat to melt them completely, not enough pressure to shatter them, just enough to change them, slowly and completely, into something new. Marble is one of the most beautiful examples. Marble begins as limestone, a sedimentary rock made largely from the compressed shells of ancient sea creatures. But when limestone is buried deeply and subjected to heat and pressure over millions of years, it recrystallizes into marble. Smooth, luminous, swirling with subtle color. One of the most prized and beautiful stones that humans have ever encountered. Slate is another example. Once a soft mudstone transformed by pressure into something smooth and cleavable, perfect for splitting into thin sheets. Schist and gneiss are others, their minerals rearranged into flowing parallel bands by the slow squeezing of the crust. There is something deeply comforting about metamorphic rocks. They remind us that transformation does not have to be sudden or violent. It can be slow, it can be quiet, it can happen in the dark, under pressure, over enormous stretches of time. And what emerges can be something genuinely beautiful. Perhaps the most relaxing thing that geology teaches us is the nature of geological time. What scientists sometimes call deep time, and just how vanishingly small our human scale of experience is within it. The Earth is approximately 4.5 billion years old. 4.5 billion years. This is a number so large that it almost loses meaning when stated plainly. So let us try to feel it rather than simply understand it. If you were to compress the entire history of the Earth into a single calendar year, if January 1st represented the Earth's formation and December 31st represented today, then all of recorded human history would occupy roughly the final 12 seconds of December 31st. The ancient Egyptians, the Roman Empire, the Renaissance, the Industrial Revolution, the entirety of the modern world. 12 seconds at the very end of a very long year. The first simple life forms appeared in this metaphorical calendar somewhere around mid-March. The first complex animals didn't appear until mid-November. The dinosaurs arose around December 18th and went extinct on December 26th. The rocks beneath your feet have been part of this entire journey. Some of the oldest rocks on Earth, the ancient cratons and shields that form the stable hearts of continents, are over 3 billion years old. They were already old when the first fish swam through Cambrian seas. They are incomprehensibly ancient by any human measure. And yet, sitting with this knowledge quietly, there is something surprisingly peaceful about it. We are not separate from this great time. We are part of it. The calcium in our bones was once part of the ocean. The iron in our blood was forged in stars that died before the Earth was born. We are not visitors to this ancient world. We are briefly and beautifully part of it. The rocks are patient. Deep time is patient. And on a quiet night, surrounded by the weight and age of the world beneath us, we can feel for a moment that same patience in ourselves. Imagine, if you will, that you are sitting on a mountain, not climbing it, not descending it, simply sitting, your back against a great cold boulder, the wind very slight and very soft, barely disturbing the thin grasses that grow between the rocks. Below you, the land falls away in long, gentle slopes. And somewhere far off, barely visible through the haze of distance, there are other mountains. And beyond those, still others. Mountains feel eternal. They feel like the most permanent things in the world. They have been the symbols of stability and endurance in cultures across human history. In myth and religion and poetry, the mountain is always there, always unchanged, outlasting everything around it. And yet, and this is one of the most gentle and extraordinary secrets in all of geology, mountains are not static at all. They are in motion. They are being raised and worn down simultaneously in a slow and stately dance that has been going on since the first continents formed, billions of years ago. Mountains are the visible expression of forces so vast and so deep that we can barely comprehend them. They are the places where the great plates of the Earth's crust have pressed against each other, crumpling the rock upward the way the edge of a tablecloth crumples when you push it across a table. Slowly, inexorably, without any hurry at all. The Earth's crust is not a single solid shell. This is a fact that took humanity a very long time to discover, and when it was finally understood, in the mid-20th century, it changed geology forever. The crust is divided into approximately 15 major plates and many smaller ones, each one a vast slab of rock that floats with extraordinary slowness on the partially molten rock of the mantle below. These plates move. They have been moving for billions of years. They move at approximately the speed that your fingernails grow. A few centimeters each year, sometimes a little more, sometimes a little less. In a human lifetime, the continents drift only a few meters from where they were when you were born. In a million years, they move perhaps 30 or 40 kilometers. And in billions of years, they have moved entire oceans. There was a time, roughly 300 million years ago, when all the landmasses of the Earth were gathered together into a single supercontinent, which geologists call Pangaea. It was surrounded on all sides by a single vast ocean called Panthalassa. If you had been able to stand somewhere in the middle of Pangaea and look in any direction, you would eventually have reached a coastline. But it might have been a very long walk. Pangaea began to break apart slowly, beginning around 200 million years ago. The plates carrying what would become North America and Europe began to separate, opening a narrow seaway that would become the Atlantic Ocean. South America began to drift away from Africa. India began its extraordinary journey northward, a slow and ancient voyage that would eventually end in a collision of almost incomprehensible force. That collision between the Indian plate and the Eurasian plate is still happening today, and it is the reason for the highest mountains on Earth. The Himalayas are, in every sense, mountains born from patience. They began to rise approximately 50 to 60 million years ago, when the Indian subcontinent, which had been drifting northward across what was then a vast tropical ocean, finally made contact with the southern edge of Asia. The collision did not happen suddenly. There was no single dramatic moment when continents crashed together. Instead, it was a gradual, grinding meeting of two immense masses of rock, each one pressing steadily against the other, the crust crumpling and thickening and rising in slow, majestic folds. Over millions of years, the rock that had once been the floor of the ancient Tethys Ocean, a shallow, warm sea that had separated India from Asia, was compressed and raised upward. Marine fossils that once rested on the ocean floor were slowly lifted toward the sky. Today, geologists find the remains of ancient sea creatures at elevations of over 5,000 meters in the Himalayas. The ocean floor became the roof of the world. Mount Everest, the highest point on Earth, is still rising. Every year, the Indian plate continues to press northward, and the Himalayas continue to grow by a few millimeters each year. At the same time, erosion works equally patiently in the other direction, wearing away the peaks with wind and water and ice. The mountain is in balance between two patient forces: the slow uplift from below and the slow erosion from above, and this balance determines the shape of the peaks, the steepness of the valleys, the way snow gathers on the ridges and ice carves the faces. The Himalayas are, in a very literal sense, a slow-motion event, a beautiful, frozen-in-time collision that has been unfolding for 50 million years and will continue for tens of millions of years more. On the other side of the world, the Andes tell a different story of mountain formation, one that involves not just collision, but fire. The Andes rise along the western edge of South America, a chain of mountains stretching nearly 9,000 kilometers from the tropics of Colombia and Venezuela all the way down to the cold, wind-swept tip of the continent. They are among the longest mountain chain on Earth, and they were born from a process called subduction. Along the western coast of South America, the oceanic plate that makes up the floor of the Pacific Ocean dives beneath the continental plate of South America. This is subduction, one plate sliding under another, descending into the mantle where it slowly melts back into magma. As the oceanic plate descends, it carries with it water and other materials that lower the melting point of the surrounding rock, generating magma that rises through the crust above. This magma feeds volcanoes. And the volcanoes, over millions of years, pile up rock and ash and lava until they become mountains. Many of the highest peaks in the Andes are volcanoes, dormant or active, their cone shapes unmistakable against the sky. Some of them, like Ojos del Salado on the border of Argentina and Chile, are over 6,000 meters tall and still occasionally release plumes of steam from their craters. Quiet reminders of the immense heat still churning below. The Andes have been rising for tens of millions of years. They have influenced the weather patterns of an entire continent, creating the Amazon rainforest on one side and one of the driest deserts on Earth, the Atacama, on the other. They are the reason the rivers of South America flow the way they do. They are the backbone of a continent built slowly by fire and pressure from below. If you could watch the continents moving, if you could accelerate time so dramatically that 1,000,000 years passed in a single second, you would see something extraordinary and strangely beautiful. The continents would drift and rotate and collide like the very slowest kind of ballet, the ocean basins opening and closing like breathing, mountain ranges rising and fading like ripples on water. Africa and South America were once pressed together so tightly that their coastlines fit together like puzzle pieces. The Atlantic Ocean, which today stretches over 4,000 kilometers, was once not there at all. It opened gradually, a crack widening over tens of millions of years, filled in by the slow upwelling of new ocean floor from the mid-Atlantic ridge, a vast underwater mountain chain where the two plates are still separating today. Australia was once joined to Antarctica. India was once an island drifting northward from a position near the South Pole. North America and Europe were once neighbors, and the rock formations on either side of the Atlantic still match each other like the torn edges of an ancient map. All of this movement, all of this slow and patient rearrangement, has been driven by the heat within the Earth's interior, the same heat that has been slowly escaping from the planet's core since the Earth first formed, 4.5 billion years ago. Convection currents in the mantle, moving even more slowly than the plates above them, create the forces that pull and push the crust in different directions. It is a system of almost unimaginable scale and almost unimaginable patience. And it is happening right now, beneath your feet, as quietly and as steadily as it always has. Mountains are not permanent, but they are patient. And in their slow rising and slower wearing away, they trace the history of a restless and beautiful planet. There is something about the sound of water that settles the mind. The soft, continuous murmur of a stream over stones. The deeper, slower sound of a wide river moving through a flat valley. Even the distant memory of water, the gentle curve of a dry stream bed, the pale smoothness of river-worn pebbles held in the palm, seems to carry with it a quality of calm. Rivers are among the most patient sculptors on earth. They do not use hammers or chisels. They use nothing more forceful than water. Water in motion, carrying grains of sand and silt and pebbles, brushing constantly against the rock below and on all sides, grain by grain, slowly carving the landscape into something new. This process is called erosion, and it is one of the great quiet forces that shape the surface of our planet. Erosion works the way time works, invisibly, continuously, without rest, and over long enough periods it can accomplish things that seem impossible. Every river begins somewhere small, a spring seeping out of a hillside, a snowfield melting in summer warmth, a collection of rainwater finding the path of least resistance down a slope. These tiny beginnings gather and merge, trickling into streams, streams merging into rivers, rivers growing wider and slower as they descend toward the sea. In its early stages, a river is energetic, not in a hurried way, but in the way of something young and finding its course. A young river flowing down a steep gradient cuts downward into its bed with remarkable effectiveness. Its water is fast enough to carry even small rocks, and those rocks scrape and grind against the riverbed as they travel, deepening the channel year by year, century by century. This is how V-shaped valleys form. The river cuts straight downward, and the valley walls are steep and close together because the river has not yet had time to widen them. Walk through a narrow mountain gorge with water rushing below and rock walls rising sharply on either side, and you are standing inside a geological argument between water and stone, one that the water is slowly, inexorably winning. But as the river descends and the gradient becomes gentler, something changes. The river, no longer cutting downward so forcefully, begins to cut sideways instead. It meanders, it curves, and the curves, once they begin, tend to grow more pronounced over time. The outer bank of each bend eroding while the inner bank builds up with deposited sediment, until the river develops those long, sinuous curves that, when seen from above, look like a ribbon of silver carelessly laid across a wide green floodplain. Mature rivers meander not because they are confused, but because the physics of water in a channel naturally tend toward curves. Each curve creates faster water on the outside and slower water on the inside, which leads to erosion on one side and deposition on the other, which deepens the curve, which intensifies the difference in water speed. And so the river slowly teaches itself to be sinuous, a lesson written in the landscape over thousands of years. Perhaps no river in the world tells the story of patient erosion more dramatically than the Colorado River, and no landscape illustrates the result of that erosion more magnificently than the Grand Canyon. The Colorado River began carving the Grand Canyon approximately 5 to 6 million years ago. A relatively recent event in geological terms, though, of course, incomprehensibly long by human measure. At that time, the Colorado Plateau, the vast flat upland through which the river flows, was rising due to tectonic forces, and the river began cutting downward to maintain its course to the sea. Over those 5 to 6 million years, the Colorado carved a canyon approximately 1.5 kilometers deep and up to 29 kilometers wide in some places. The river used sand and gravel and rocks as tools, grinding away at the rock below with the patience of something that has no concept of time at all. The walls of the Grand Canyon tell the story of nearly 2 billion years of Earth history. The oldest rocks at the bottom of the canyon, the Vishnu schist, dark and crystalline, are some of the most ancient rocks in North America, formed nearly 2 billion years ago. Above them, layer by layer, the rock record climbs through time: limestone from ancient seas, sandstone from desert dunes, shale from quiet mudflats, each layer representing a different chapter in the story of this part of the world. To stand at the rim of the Grand Canyon as the sun sets, watching the shadows move slowly across the layers of colored stone, buff and pink and pale orange and deep red, is to feel, without quite being able to articulate it, the weight and depth of time. The canyon is not just a hole in the ground. It is an open book, written in stone with 2 billion years worth of pages. And the river that made it, still flowing at the bottom, still carrying its load of sand and gravel, still grinding quietly away, is still writing. Rivers do not only carve, they also build. All the material that a river erodes from the land upstream, the sand, the silt, the clay, is not simply lost. It is carried downstream and eventually deposited somewhere. This process of transportation and deposition is one of the great geological gifts that rivers offer to the world. Where a river flows through a wide, flat valley, it periodically overflows its banks during times of heavy rain or snowmelt. This flooding deposits a thin layer of rich, fine sediment across the floodplain. What farmers have understood for thousands of years as the source of the most fertile soil on Earth. The annual flooding of the Nile, celebrated and depended upon by ancient Egyptians for millennia, was a geological process. The river carrying sediment from the highlands of Ethiopia and depositing it across the fields of Egypt. And where a river finally meets the sea, after its long journey from mountain to coast, it deposits its remaining sediment load in a spreading fan shape called a delta. The Mississippi Delta, the Nile Delta, the Ganges-Brahmaputra Delta. These are vast, flat, marshy landscapes built entirely from sediment that rivers carried from distant mountains and laid down, grain by grain, over thousands of years. The Ganges-Brahmaputra Delta, which forms the coastal region of Bangladesh and part of West Bengal, is one of the largest river deltas in the world. Much of its land sits barely above sea level, and it is still growing, still being built slowly by the sediment carried down from the Himalayas by these great rivers. The mountains that were raised by the collision of continents are being slowly, grain by grain, transported to the sea. Everything is connected: the mountain and the delta, the rain and the rock, the slow uplift of the crust, and the slow, patient carrying of sediment to the sea. It is all one great cycle, unfolding in geological time, quiet and continuous and endlessly beautiful. Not all rivers are visible. Some of the most extraordinary river systems on Earth flow not across the surface, but beneath it, moving through the darkness of cave systems and porous rock in silence and in secret. In limestone landscapes where the rock is soluble in slightly acidic rainwater, rivers can disappear entirely underground, vanishing into cracks in the rock and flowing through passages and caverns that they themselves have carved over thousands of years. These underground rivers can travel for many kilometers before surfacing again in a spring or a resurgence, emerging from the hillside as if from nowhere, clear and cold and quiet. The Puerto Princesa subterranean river in the Philippines is one of the world's most remarkable underground rivers. Flowing through a cave system with a navigable channel of over 8 kilometers, with cathedral-like chambers and extraordinary rock formations created by the long, slow work of water on limestone. These hidden rivers remind us that the landscape has layers, that what we see on the surface is only part of the story, and that beneath us, invisible and quiet, the water continues its ancient work of carving and shaping and dissolving in the patient dark. The ground beneath your feet is not simply solid, it is layered, complex, full of life and movement and secret architecture that most of us never think about as we walk across it. Below the surface of the earth lies a world as rich and varied as anything visible above. A world of stacked geological layers, of water moving through stone, of living organisms and long dead ones, of spaces and passages and structures that have taken millions of years to form. If you could somehow slice through the ground directly beneath you, peel back the landscape like a cross-section in a textbook, you would find layers that tell the entire history of the place you are standing. The story of the soil, the story of the rock beneath it, the story of the water that moves through everything, the story of the heat rising from the deep interior of the earth. Let us descend quietly and gently through those layers. The very top layer, the one that plants root in, that worms move through, that rain soaks into, is soil. And soil, for all that it seems ordinary, is one of the most extraordinary substances on Earth. True topsoil, the dark, crumbly, rich layer that sits at the surface in healthy landscapes, is not simply ground-up rock. It is a mixture of mineral particles, water, air, organic matter, and an almost unimaginably dense community of living organisms. A single teaspoon of healthy topsoil contains more microorganisms than there are people on Earth. Billions of bacteria, thousands of fungi, protozoa, nematodes, and countless other tiny living things, all working in concert to break down organic matter, cycle nutrients, and create the conditions in which plants can grow. Soil forms very, very slowly. A centimetre of topsoil can take between 100 and 1,000 years to form, depending on the climate and the type of rock below. It forms as rock is slowly broken down by weather, by the freezing and thawing of water in cracks, by the chemical action of weak acids in rainwater, by the physical abrading of wind-blown particles, and as organic matter accumulates and is decomposed and mixed into the mineral material. Below the topsoil is the subsoil, lighter in color, less rich in organic matter, but still containing clay particles and minerals and the roots of deep-rooting plants. Below that is the parent material, partially weathered rock, the material from which the soil above it formed, and below that, the bedrock. Each layer represents a different stage of the great, slow transformation of rock into soil, a process that takes centuries at its fastest and millions of years at its most complete. Moving deeper, we come to one of the most important and most overlooked geological features of the world: aquifers. An aquifer is a body of permeable rock or sediment through which groundwater moves and collects. Aquifers can be found almost everywhere on Earth. Beneath deserts, beneath cities, beneath farmland, beneath mountains, they hold an enormous fraction of all the fresh water on Earth, far more than all the rivers and lakes on the surface combined. The largest known aquifer in the United States is the Ogallala Aquifer, also called the High Plains Aquifer, which underlies approximately 450,000 square kilometers of the Great Plains. It is a vast, silent reservoir of water, collected over thousands of years as rain and snowmelt slowly percolated down through the soil and rock above. In some aquifers, the water moves. Very slowly, often just a few meters per year, groundwater flows through the pores and cracks of the rock, following gravity and pressure gradients towards springs and streams and wells. In other aquifers, confined aquifers where permeable rock is sandwiched between impermeable layers, the water sits under pressure, and when a well is drilled into it, the water rises up naturally, sometimes all the way to the surface. These are called artesian wells, and the water they produce has been underground for sometimes thousands of years. Ancient water, old beyond living memory, finally returning to the surface. There is something deeply peaceful about aquifers, about the idea of all that water, quietly at rest beneath the surface, held in the darkness of stone, patient and still. Deeper still, we may encounter caves, the secret interior architecture of the earth, spaces that human beings have explored with wonder and reverence since our earliest ancestors first ventured into the earth with firelight. Most caves form in limestone, through the same slow process of dissolution that carves underground rivers. Rainwater, slightly acidic from absorbing carbon dioxide as it falls through the air, percolates down through the soil and into the limestone below. Over thousands of years, it dissolves the calcium carbonate of the limestone along fractures and bedding planes, gradually widening them from hairline cracks to passages to rooms to great caverns. The process is extraordinarily slow. A cave passage that a person could walk through might have taken 100,000 years to dissolve out of the rock. The great chambers of show caves, the enormous cathedral-like spaces that tourists visit in places like the Mammoth Cave System in Kentucky or the Scotian Caves in Slovenia, took far longer than that. Inside these caves, in the dark and quiet and constant temperature, another kind of slow and patient creation is taking place. The building of speleothems, cave formations. Stalactites hang from ceilings where calcium-rich water drips with extraordinary slowness from above. Stalagmites grow up from the floor where those same drips land. Over thousands of years, if the two grow close enough, they may eventually join into a column, a pillar of stone that has been growing since before humans invented writing. The rate of speleothem growth varies enormously with climate and the chemistry of the water. In some caves, the formations grow less than a millimeter per year. A stalactite that is 1 meter long may be over 10,000 years old. Imagine standing in a cave and looking up at stalactites, knowing that each one has been growing since the last ice age, each drip adding an invisible layer of mineral year by year in the dark. There is no hurry here. There is no noise but the occasional soft sound of a drip falling from stone to stone. There is only time and patience and the quiet miracle of mineral slowly becoming form. Below the caves, below the aquifers, we reach rock that has not seen light or air since the Precambrian era. Rock so old that the world above it would be unrecognizable. So ancient that it formed when even the oceans were young. The cratons, the ancient, stable cores of the continents, are made of rock that has not been significantly disturbed for billions of years. They have survived everything: the collision and breakup of supercontinents, the passage of ice, ages, the impact of ancient meteorites, the slow wearing away of mountain ranges above them. They are the most enduring features of Earth's surface, the foundations upon which everything else has been built and rebuilt over geological time. In places like the Canadian Shield, the Scandinavian Shield, and the Pilbara Craton of Western Australia, these ancient rocks emerge at the surface, dark and worn smooth by billions of years of erosion, some of them containing the oldest minerals on Earth. Tiny crystals of zircon found in the Jack Hills of Western Australia have been dated to approximately 4.4 billion years old. Almost as old as the Earth itself, they were already crystals when the Moon formed. They were already ancient when the first oceans gathered on the surface of the young planet. To hold one of these ancient zircon crystals, barely visible to the naked eye, a speck of glittering mineral, would be to hold something that has endured for almost the entire history of our planet. Something that was present at the very beginning of the story we are still living. The world beneath our feet is deep and ancient and full of quiet mystery. Every step we take carries us over geological worlds we will never see. But knowing they are there, the soil, the aquifers, the caves, the ancient rock, is somehow deeply reassuring. The ground beneath us has a history that makes our own histories seem bright and brief and precious. There are mountains in the middle of continents where, if you look closely at the rock, you will find shells. Not the shells of land animals, but the shells of creatures that lived in the sea. Clams and sea urchins and corals and ammonites, pressed into limestone or shale, perfectly preserved, looking for all the world as though they might have just washed up on a beach yesterday. But they did not wash up yesterday. They were buried in sediment on the floor of an ocean that may have covered this land for hundreds of millions of years. And when the ocean retreated and the land rose and the rock was compressed and lifted and eventually exposed at the surface, it carried with it this extraordinary testimony. Here was the sea. Here, where you are standing now, there was once deep and quiet water, and creatures living and dying in it, and their bodies settling slowly to the floor. Fossils are among the most quietly amazing things in all of geology. They are windows into worlds that no longer exist, preserved by processes that had to be exactly right, at exactly the right moment, maintained for millions or hundreds of millions of years, by the simple act of being buried in the right kind of rock. The formation of a fossil is, in itself, a story of patience and precision. When an organism dies, it is almost always consumed or decomposed by scavengers, by bacteria, by the simple chemical processes of decay. The vast majority of every creature that has ever lived has left no trace whatsoever in the geological record. They lived and they died, and they returned entirely to the world that made them. But occasionally, very occasionally in geological terms, conditions are exactly right for preservation. An organism dies in a quiet, low oxygen environment where decay is slowed. Its body is quickly buried in fine sediment, soft mud, gentle ash, settling sand, before it can be disturbed. Over time, the sediment hardens into rock around the organism's remains. The soft tissues decay, but the hard parts, bones, shells, teeth, wood, are preserved as cavities in the rock or replaced gradually by minerals that crystallize into the exact shape of the original structure. This process, permineralization, is the most common way that fossils form. Mineral-rich groundwater percolates through the sediment, slowly replacing the original material of the bone or shell with minerals like silica or calcite, atom by atom, over thousands of years, until what remains is rock that has precisely the structure and appearance of the original organism. The result is a fossil, a portrait of life made in stone, preserved for millions of years, waiting patiently in the dark for someone to find it. Of all the rocks that contain the memory of ancient oceans, limestone is perhaps the most widespread and the most quietly remarkable. Limestone is a sedimentary rock made largely of calcium carbonate, the same material that makes up seashells and coral skeletons. In warm, shallow tropical seas, organisms have been building calcium carbonate structures, shells, skeletons, reefs, for hundreds of millions of years. When these organisms die, their hard parts settle to the seafloor, accumulating in layers. Over millions of years, compressed and cemented together by the weight of sediment above, these accumulations become limestone. Much of the limestone exposed at the Earth's surface today formed in exactly this way, in ancient shallow seas, from the compressed remains of organisms that lived in warm, clear water under a very different sky. The white cliffs of Dover, those iconic chalk cliffs of southern England, are made of a fine-grained limestone composed almost entirely of the microscopic shells of tiny sea creatures called coccolithophores, organisms that were already ancient by the time the dinosaurs walked the Earth. The thickness of the chalk at Dover is over 400 meters. Every centimeter of it represents the accumulation of millions of those tiny shells, settling through the water of an ancient sea that covered much of what is now Europe. The rate of chalk accumulation was perhaps a centimeter or two per 1,000 years. 400 meters of chalk represents an almost incomprehensible span of quiet time. Limestone landscapes, karst landscapes, have a particular quality of quiet beauty. The rock dissolves in rainwater, creating smooth, rounded hills and closed depressions, and below the surface, the caves and passages described earlier. Whole regions of the world are defined by their limestone foundations. The Dordogne Valley in France, where the cave paintings of Lascaux hide in chambers that ancient seas carved long before the first human. The karst towers of Guilin in southern China, which rise like grey-green pillars from the mist of the Lee River Valley. The limestone pavement of Yorkshire in England, where blocks of pale stone are divided by deep, narrow crevices called grikes, each one its own tiny world of shade and moisture and delicate ferns. Among the most beautiful and most commonly found fossils in marine limestone are ammonites, coiled spiral-shelled animals that lived in the seas from about 400 million years ago until the mass extinction 66 million years ago that also ended the dinosaurs. Ammonites were cephalopods, relatives of the modern nautilus and, more distantly, squid and octopus. They lived in the outer chamber of their coiled shell, and the shell itself was divided into many smaller chambers that the animal could fill with gas or liquid to control its buoyancy, allowing it to hover at different depths in the ancient sea. When ammonites died, their shells often sank to the seafloor and were buried in the sediment. Over millions of years, they were fossilized, and today they are among the most widespread and beautiful fossils in the geological record. Ammonite fossils can be found in limestone and shale beds across Europe, North Africa, North America, and many other parts of the world. Coiled, spiral, often beautifully preserved, ranging in size from a fingernail to several meters across. To hold an ammonite fossil is to hold something that was alive in the Jurassic Sea, something that swam slowly, gracefully, adjusting its depth with the subtle regulation of gas in its chambers. Through a world where the continents were arranged differently, where the climate was warmer, where the creatures on land were unlike anything alive today. It is a connection across such a vast gulf of time that it barely seems possible. And yet the stone does not lie. The ammonite was here, and now, in your hand, it is here again. Coral reefs are among the most biologically rich environments on Earth today, but they are also, in their fossilized form, among the most important records of ancient ocean environments in the geological record. Fossil coral reefs can be found in limestone formations all over the world, sometimes thousands of kilometers from the nearest ocean. They tell us where ancient seas once stood, what the water temperature and chemistry was, how deep the water was, and how life on Earth has changed over hundreds of millions of years. The Devonian period between about 400 and 360 million years ago is sometimes called the Age of Fishes, but it might equally well be called the Age of Reefs, because at that time, enormous coral reefs covered vast areas of the shallow tropical seas that covered much of what is now Europe and North America. These reefs and the organisms that built them form a major component of the limestone found in much of Europe and eastern North America today. The next time you stand before a limestone wall, even the wall of a building if the stone has been left unpolished, look closely. You may see the shadows of ancient creatures in the rock, a fragment of coral, the cross-section of a shell, a trace fossil. The burrow of a worm that moved through soft seafloor sediment 300 million years ago, preserved now as a ghostly loop in the stone. Ancient oceans turned to stone. The sea is not always where we expect to find it. There is a slow fire at the heart of the world. It has been burning since before the Earth was fully formed, since the time when the young planet was still accreting from the cloud of dust and rock that swirled around the young sun, and the energy of all that impact and all that compression generated heat that has been slowly, very slowly, radiating outward ever since. The Earth's interior is hot, incomprehensibly, extraordinarily hot. At the very center, the inner core, a ball of solid iron and nickel about the size of the moon, temperatures may reach 5,000 degrees Celsius. The outer core surrounding it is liquid metal, churning slowly in convection currents driven by temperature differences. And it is this churning that generates Earth's magnetic field. Above the core, the mantle, a vast shell of rock almost 3,000 kilometers thick, is technically solid, but at geological timescales, it behaves almost like a very viscous fluid, slowly flowing in enormous convection cells that take millions of years to complete a single circuit. And above the mantle, thin and comparatively fragile, is the crust, the surface we live on, the plates that slowly drift, the mountains and valleys and ocean floors that make up our familiar world. Volcanoes are the places where the Earth's inner heat makes itself most dramatically visible. But even a volcano, examined carefully, is more patient than it appears. A volcano is not simply an explosion waiting to happen. It is a complex, evolving geological system with a life cycle that spans thousands to millions of years. Most volcanoes form above subduction zones, where one plate descends beneath another, or above hotspots where a particularly hot region of the mantle melts rock and sends magma upward through the crust. In either case, the process begins far below the surface, in chambers of partially molten rock called magma chambers that slowly accumulate magma over years, decades or centuries. The magma rises because it is less dense than the surrounding rock. Like bubbles rising slowly through a very thick liquid, it finds pathways upward through cracks and fractures, moving perhaps a few meters per day in an active eruption, but much more slowly at other times. Perhaps a few meters per year as the magma chamber slowly fills. When conditions are right, when enough pressure has accumulated, when the magma reaches the surface through conduits and vents, an eruption occurs. But even an eruption, which can seem sudden and violent, is often the culmination of a very slow process. And many eruptions are not the explosive events that dominate popular imagination, but rather quiet, persistent outpourings of lava that build up the volcanic edifice layer by layer over thousands of years. The shield volcanoes of Hawaii, Mauna Loa and Kilauea, are among the most active volcanoes on Earth, and yet their eruptions are often surprisingly gentle. Fluid basaltic lava flows slowly down the flanks of the volcano, glowing orange and red in the dark, moving at walking pace or slower, cooling and hardening at its edges as the still molten interior continues to flow. Over hundreds of thousands of years, these slow outpourings of lava have built up the Hawaiian Islands from the seafloor, a process still ongoing. Mauna Loa, measured from its base on the ocean floor, is taller than Mount Everest. It was built not by any single catastrophic eruption, but by the patient accumulation of lava flow after lava flow, year after year, for millions of years. Hawaii sits above what geologists call a hotspot, a place where a plume of unusually hot mantle material rises from the deep earth, penetrating the plate above and generating magma that feeds the volcanic activity. What makes hotspots particularly fascinating is that they are fixed, or very nearly so, while the plate above them moves. As the Pacific plate slowly drifts northwestward over the Hawaiian hotspot, new volcanic islands form above the hotspot, while older ones drift away from it and slowly subside back into the ocean. This is why the Hawaiian Islands form a chain, with the oldest islands to the northwest and the youngest, Iuandia, including the Big Island, which is still growing as we speak, to the southeast, directly above the hotspot. Even farther to the northwest, the islands become progressively smaller, more eroded, and eventually disappear beneath the surface as they cool and subside. The chain continues underwater as a series of seamounts, former islands that have sunk below the waves over millions of years. The entire Hawaiian Emperor chain, including both the islands above water and the submerged seamounts, stretches nearly 6,000 kilometers across the Pacific Ocean. The oldest seamounts at the northern end of the chain are approximately 80 million years old. The chain is, in a very literal sense, a record of the Pacific Plate's slow movement over the fixed hotspot, a geological timeline written in islands. When lava cools and solidifies, the result is often basalt, a dark, fine-grained igneous rock that is, by volume, the most common rock type on Earth's surface. Most of the ocean floor is basalt, created by the continuous outpouring of lava from mid-ocean ridges where plates are separating. The mid-ocean ridges are, in their quiet way, the most volcanically active features on Earth. They form a system of underwater mountain ranges extending 60,000 kilometers around the planet, longer than any other mountain range by far, where the spreading plates pull apart and magma wells up from below to fill the gap. At the mid-ocean ridges, the ocean floor is created. New basalt solidifies, cools, and becomes part of the oceanic plate, which then slowly moves away from the ridge. The ocean floor is thus continuously renewed. And since new floor is always being created at the ridges, older floor must be continuously consumed at the subduction zones, where it descends back into the mantle. The age of the ocean floor therefore increases systematically with distance from the ridges. The youngest ocean floor is right at the ridge, newly formed, sometimes still warm. The oldest ocean floor, before it reaches a subduction zone, is about 200 million years old. Compared to continental rock, the ocean floor is geologically young. This is a sobering thought. The ocean floor, which covers more than 70% of Earth's surface, is in continuous, slow, patient renewal. All the ancient ocean crust that has ever formed has long since descended back into the mantle and been remade. Beneath the extraordinary landscape of Yellowstone, the geysers, the hot springs, the boiling mud pools, the extraordinary color palette of thermophilic bacteria in the thermal waters, lies one of the largest volcanic systems in the world. The Yellowstone caldera, sometimes called a supervolcano, sits above a hotspot that has been active for at least 17 million years. The caldera itself a vast depression in the landscape formed by the collapse of a magma chamber after a catastrophic eruption approximately 640,000 years ago, is roughly 72 by 55 kilometers across. But even at Yellowstone, the drama is more geological than theatrical. The geysers that shoot columns of water and steam into the sky, including Old Faithful, which has been erupting approximately every 90 minutes for as long as reliable records have been kept, are expressions of the slow, patient heat rising from below, warming groundwater that circulates through the rock, building pressure in narrow conduits until the water flashes to steam and erupts. The colors of the hot spring pools, the vivid blues and greens and oranges and yellows, are painted by communities of thermophilic microorganisms, bacteria and archaea, that thrive in water that would be fatal to most life, living at temperatures between 40 and 90 degrees Celsius, sustained by the chemicals dissolved in the volcanic water. Yellowstone is a place where the Earth's inner warmth rises close enough to the surface to be felt and seen. A reminder that the fire at the heart of the world is still burning, still patient, still slowly working its way toward the surface wherever it finds an opening. There is nothing to fear from this. The Earth has been doing this for 4.5 billion years. It breathes slowly and deeply through its volcanoes and its thermal springs, releasing a little of its inner warmth into the surface world, and then settling back into its long, quiet contemplation of geological time. Every grain of sand has a story, a long one. Hold a single grain of sand, if you can imagine it, balanced on your fingertip, barely visible, a tiny speck of pale mineral no bigger than a pinhead. This grain has been on a journey that may have taken millions of years. It began, most likely, as part of a rock, a crystal of quartz embedded in granite or sandstone or some other stone, locked in place, surrounded by other minerals, deep within the earth or forming the fabric of a cliff face. Over time, the rock was exposed at the surface. Rain fell on it. Water seeped into the tiny cracks around the quartz crystals and froze, expanding slightly, widening the cracks. The rock began to break apart, slowly, imperceptibly, over centuries. And eventually, the quartz crystal was freed. Now it was a pebble. And then, carried by rain or gravity or a stream, it began to move. It tumbled and bounced and rolled, striking other rocks, losing its rough edges, gradually becoming rounder and smoother. It was carried by a river toward the sea, and along the way the river's current abraded it further, wearing it down grain by grain to a smaller and smaller size. By the time it reached the sea, it was sand. Sand is not a single thing. It is a size, technically. Any mineral or rock particle between approximately 0.0625 and 2 millimeters in diameter qualifies as sand. But the composition of sand varies enormously from place to place, depending on the type of rock being eroded and the processes that have shaped the landscape. The most common ingredient in most sand is quartz. Quartz is silicon dioxide, one of the most abundant compounds in the Earth's crust, and it is extraordinarily hard and chemically resistant. When rocks are weathered and broken down, many of their constituent minerals dissolve or decompose, but quartz survives. It is the last mineral standing, the hardest traveler, the one that makes it all the way from mountain rock to ocean beach with its structure intact. This is why most beach sand and desert sand is predominantly quartz. After billions of years of weathering, the minerals that were less resistant have been removed, and what remains is the most durable residue of the continents, mostly quartz, smoothed by its long journey, polished to a pale gleam by the waves or the wind. But not all sand is quartz. Some beaches are made of entirely different materials. The black sand beaches of Hawaii and Iceland are made of basalt. volcanic rock that has been broken down by the waves before it had time to be reduced to quartz grains. The pink sand beaches of Bermuda owe their color to the shells and skeletons of foraminifera, tiny single-celled organisms with pink calcium carbonate shells mixed with the carbonate sand. The green sand beaches of Papacolia, Hawaii, are made of olivine, a greenish mineral that crystallizes in basaltic lava. And the white sand beaches of the tropics, those impossibly white, impossibly fine beaches that seem to glow in the sun, are often made not of quartz at all, but of calcium carbonate from the broken down shells and skeletons of coral reef organisms. Coral reef sand. The compressed and tumbled remains of an ancient and still living ecosystem. Sand does not only travel by water. In the great deserts of the world, it travels by wind. A desert is, at its simplest, a place where evaporation exceeds precipitation, where more water is lost from the surface than falls on it. Deserts can be hot, like the Sahara and the Arabian Desert, or cold, like the Gobi in Central Asia or the polar deserts of Antarctica. But what many deserts have in common is wind. And wind, in the absence of vegetation to hold it in place, moves sand. The way wind moves sand is a quiet and beautiful process. In the lightest breezes, sand grains roll or slide along the surface, nudging each other, slowly creeping forward. In stronger winds, grains are lifted briefly into the air and then dropped again, bouncing and ricocheting across the surface in a process called saltation. Each grain disturbing others when it lands, keeping the entire surface in low, continuous motion. Over time, this wind movement sorts and shapes the sand into dunes, those beautiful, smooth, curving forms that seem to flow across the desert landscape like slow waves of stone. Dunes have shapes that are determined by the direction and consistency of the wind. Crescent-shaped barcans form where wind blows consistently from one direction. Star dunes form where winds shift in multiple directions. Long linear dunes called seifs extend for hundreds of kilometers parallel to the prevailing wind. The Great Erg, a sandy sea of dunes, of the Sahara Desert covers approximately a quarter of the Sahara's total area. The dunes rise in some places to heights of nearly 200 meters, their smooth faces carved and shaped by winds that blow across thousands of kilometers of open desert. The sand moves slowly but continuously, shifting a few meters each year in the direction of the prevailing wind. But dunes also slow the wind and build up in particular places, and some dune systems have been in roughly the same location for tens of thousands of years. Their shape changing with each storm, but their presence remaining, a stable feature of the desert landscape. Here is one of the most quietly extraordinary facts about sand. Sometimes it sings. In certain dune fields around the world, the Kelso Dunes in California, the Congarin Els in Mongolia, dunes in the Arabian Peninsula and coastal Peru, the sand produces a deep, resonant humming or booming sound when the surface layers avalanche or are disturbed. The phenomenon is called singing sand or booming sand, and it has been known to travelers in desert regions since ancient times. The sound is produced by the coordinated movement of billions of sand grains sliding over each other in unison. The grains must be almost exactly the same size and shape, the highly sorted, well-rounded quartz grains that form after a very long journey of weathering and transport. And the surface must be dry. When all conditions are right, the vibrations of the grains synchronize, creating a resonance that can last for minutes and can be heard from kilometers away. A desert that sings, billions of years of patient geology, the weathering of mountains, the long journey of rivers, the sorting action of wind, culminating in something that sounds almost like music. Quartz, the mineral that most sand is made of, has other extraordinary properties. It is piezoelectric, meaning that it produces an electric voltage when mechanically stressed, and vice versa. This property makes quartz crystals extraordinarily useful in watches and clocks, where a tiny piece of quartz vibrates at a precise and predictable frequency when an electric current is applied, keeping time with remarkable accuracy. The quartz in your watch, or in the clock on your phone, is the same mineral that makes up most of the sand on Earth's beaches. It has the same crystal structure, the same silicon and oxygen atoms arranged in the same geometric pattern. Whether it is a grain of beach sand or a precision-cut crystal in a timepiece, timekeeping and geological time, connected by a grain of quartz, the mountain becomes, the river becomes, the beach becomes, the dune becomes, in its smallest and most precise form, the keeper of seconds. There is a kind of silence that only exists in certain cold places. A silence that is more than just the absence of sound. It is the presence of something vast and still and ancient. You can hear it, if you are quiet enough, in the mountains where glaciers move. It is the silence of ice, of compressed snow that fell perhaps 1,000 years ago and has been slowly transforming ever since. Glaciers are among the most patient things on Earth. They move with an unhurriedness that makes rivers seem frantic by comparison. A glacier may advance only a few centimeters per day in its fastest section, and many glaciers move considerably less than that. And yet, given enough time, their effect on the landscape is as profound as any force in geology. Glaciers carve, they grind, they transport, they deposit. And they do all of this with the slow, inexorable patience of something that weighs billions of tons and cannot be stopped by any obstacle smaller than a mountain range. A glacier begins as snow. In places where more snow falls in winter than melts in summer, the snowfall accumulates year after year, layer by layer, compressing under its own weight. Fresh snow is light and airy, full of empty space. As it accumulates and compresses, the air is squeezed out and the snow crystals recrystallize into something denser and more solid, first granular ice called firn, and eventually, after enough years and enough compression, into glacial ice. Glacial ice is different from the ice you might find in a glass of water. It is denser, more plastic, and has a subtle blue tint that comes from the absorption of red wavelengths of light and the scattering of blue. Old glacial ice, ice that has been compressed for hundreds of years, is extraordinarily clear and pure, free of the air bubbles that give younger ice its cloudy appearance. Light travels through it differently, and the result is that color of deep, quiet blue that you sometimes see in the interior of a crevasse or at the face of a calving glacier. When enough ice accumulates, it begins to move, not because it melts and flows, though there is often a thin film of meltwater at the base of a glacier that aids its movement, but because ice under sufficient pressure behaves plastically, deforming slowly and flowing under its own weight. The ice in a glacier is actually moving very slowly downslope in the way that a very thick liquid moves. For most of Earth's history, the planet has been warmer than it is today, and the polar regions have been largely free of ice. But at certain periods in geological history, driven by slow, complex changes in Earth's orbit, in the distribution of continents, and in the composition of the atmosphere, the climate has cooled enough for ice sheets to advance from the poles and cover large portions of the continents. We are currently living in an ice age in the broad geological sense. The polar ice caps, particularly the Great Ice Sheet of Antarctica, which covers an area larger than the continental United States to an average depth of over 2 kilometers, are a feature of a glacial period. Even the term ice age has a loose meaning. Geologists use it to describe a long period of glacial and interglacial cycles, and in this sense we have been in an ice age for about 2.5 million years. Within that ice age, the climate has oscillated between cold glacial periods, when ice sheets extended far into North America, Europe, and Asia, and warmer interglacial periods like the one we currently occupy. The last glacial maximum, when ice sheets reached their greatest extent in the current ice age, was approximately 20,000 years ago. At that time, the Laurentide ice sheet, the great ice sheet that covered much of North America, extended southward to approximately the present-day location of New York City and the Ohio River. The ice was, in places, 3 to 4 kilometers thick. The weight of it depressed the crust beneath by hundreds of meters. So much water was locked up in ice that sea levels were approximately 120 meters lower than they are today, exposing vast areas of continental shelf as dry land. Britain was connected to continental Europe across what is now the North Sea. Australia and New Guinea were connected. Southeast Asia extended much farther than it does today, with a vast landmass that has been given the name Sunderland. People could walk from Siberia to Alaska. Then, slowly, the climate warmed. The ice retreated. The meltwater raised the seas. The land, relieved of the crushing weight of the ice, slowly rose back. A process called isostatic rebound that is still happening in places like Scandinavia and Canada, where the land is rising several millimeters per year as it recovers from the weight of ice that melted 10,000 years ago. The ice ages are not ancient history. Their signature is written all over the modern landscape. Among the most spectacular legacies of glacial erosion are fjords, long, deep, narrow inlets of the sea that form where glaciers carved valleys below sea level, which were then flooded as the ice retreated and the sea rose. Norway is the most famous land of fjords. The Sognefjord, Norway's longest, extends over 200 kilometers inland from the coast. Its walls rise nearly 2,000 meters above the water surface, and the water itself is over 1,300 meters deep in places. It is a valley of almost inconceivable scale, carved by a glacier over tens of thousands of years. Fjords are also found in New Zealand's South Island, the spectacular Milford Sound and Doubtful Sound of Fjordland, and in Chile, Greenland, Iceland, and Alaska. Each one is a record of glacial power and patience, carved when the ice was thick and moving slowly but irresistibly through the landscape. The glacier that carved a fjord was, itself, once a mountain glacier that grew and expanded over thousands of years before finally reaching the coast. It carved its valley with the tools at its base, rock fragments frozen into the ice, grinding against the bedrock below with immense pressure. And as it deepened the valley, it exposed fresh rock to continue the process. Where glaciers have moved through mountain landscapes and then melted away, they have left behind valleys that are distinctively different from those carved by rivers. River valleys are V-shaped, narrow at the bottom, widening upward, with the river at the lowest point. But glaciated valleys are U-shaped, broad and flat at the bottom, with steep, almost straight walls rising on either side. The difference in shape reflects the different way that glaciers and rivers erode. A river cuts downward primarily, while a glacier, which fills the entire valley from wall to wall, erodes both downward and sideways simultaneously. One of the most charming features of glaciated mountain landscapes is the hanging valley. A smaller valley, tributary to a larger one, whose floor is now suspended high on the valley wall, because the main glacier carved its valley much more deeply than the smaller tributary glacier could manage. Waterfalls often cascade down the walls of glaciated valleys from these hanging tributaries. Yosemite Valley in California is famous for exactly this landscape, with waterfalls like Yosemite Falls and Bridal Veil Fall plunging from hanging valleys into the flat-floored main valley below. Yosemite Valley itself is one of the finest examples of a glaciated valley in the world. The flat valley floor, the smooth, rounded domes of granite above, the vertical walls of Half Dome and El Capitan. All of these features reflect the work of glaciers that occupied this valley multiple times during the Ice Ages, carving and polishing and shaping the landscape into the form it holds today. The glaciers are long gone from Yosemite, but their work remains polished and patient, waiting quietly for the next visitor to look up and wonder. Deep in the darkness of the earth, in cavities and pockets within the rock, something extraordinary has been happening for millions of years. Not fire, not movement, not the grinding of plates. Something much quieter than that. Crystals are growing. They grow without light and without sound. They grow in water so slow-moving that it barely qualifies as a flow. They grow atom by atom, ion by ion, each new molecule finding its correct position in the lattice and settling there with a kind of molecular precision that no human engineer could match. They grow over thousands, sometimes millions of years. And the result is something of such geometric perfection and natural beauty that humans have been captivated by crystals since the earliest times. A crystal is simply a solid material whose atoms are arranged in a highly ordered, repeating three-dimensional pattern called a crystal lattice. The shape of the crystal, the angles of its faces, the symmetry of its form, directly reflects the geometry of the underlying atomic arrangement. Quartz crystals are hexagonal because the silicon and oxygen atoms that make up quartz naturally arrange themselves in a hexagonal pattern. Salt crystals are cubic because sodium and chloride ions naturally arrange themselves in a cubic lattice. Every crystal's shape is, in a sense, a portrait of its atomic architecture, made visible at human scales. Quartz is the most abundant mineral in the Earth's crust, and perhaps the most familiar crystal to most people. It comes in an extraordinary variety of forms and colors, each one determined by trace impurities or by conditions during formation. Pure quartz, when it grows slowly enough in the right conditions, forms clear, glass-like hexagonal prisms with pyramidal terminations. The classic clear quartz crystals that are among the most recognizable of all minerals. When iron is present in trace amounts, quartz becomes purple, the variety known as amethyst. When manganese and iron are present together in different proportions, the quartz may be pink, rose quartz. When inclusions of rutile needles are present, the quartz may appear to contain fine golden threads, rutilated quartz. Amethyst, perhaps the most beloved of the quartz varieties, forms in cavities within volcanic rock called geodes. When lava solidifies and shrinks, it sometimes leaves gas bubbles or spaces within the rock. Over millions of years, silica-rich fluids percolate through these spaces, and amethyst crystals slowly grow inward from the cavity walls. Their purple color deepening with iron content and the intensity of natural radiation from the surrounding rock. A geode cut open reveals this hidden world, an outer shell of plain gray volcanic rock, and an interior lined with a glittering, purple galaxy of amethyst crystals, each one perfectly formed, catching the light and sending it back in 1,000 tiny gleams. From the outside, the geode looks like nothing more than an unremarkable rounded stone. Its secret is entirely interior. This too is a geological parable of patience. The best things are sometimes hidden in the plainest exteriors, and their beauty requires time, an almost incomprehensible amount of time, to develop. One of the most extraordinary discoveries in the history of mineralogy was made in the year 2000, when miners exploring a silver mine in Nacre, in the Chihuahua Desert of Mexico, broke through into a cave that had been sealed for hundreds of thousands of years. The Cave of Crystals, as it came to be called, contains some of the largest natural crystals ever found on Earth. The crystals are selenite, a form of gypsum, calcium sulfate, and they are enormous. Some are over 11 meters long and weigh over 50 tons. They fill the chamber in a forest of translucent white pillars, crossing each other at angles, their smooth surfaces glowing with a soft luminescence in the light of explorers' lamps. These crystals formed over approximately 500,000 years in a pocket of water trapped below the mine. Water that remained at a remarkably stable temperature of about 58 degrees Celsius, just warm enough to keep the gypsum in solution, but not so warm that it prevented crystallization. In these conditions, the crystals grew at an extraordinarily slow rate, perhaps a few centimeters per 1,000 years, but without interruption, accumulating their enormous size over 500,000 years. They are the result of 500,000 years of absolute patience in darkness and warmth and silence, growing toward a perfection of form that no one saw until the moment the miners broke through. The cave could not be explored without special cooling suits, because the temperature and humidity would otherwise cause the human body to overheat rapidly. The crystals are so fragile, stable only at their formation temperature, that exposing the cave to the cooler air of the mine has already begun to etch and damage their surfaces. The Cave of Crystals is a place that spent 500,000 years becoming itself, only to be discovered in the very moment that its encounter with the human world began to change it. Calcite is another extraordinarily common and beautiful mineral. It is the primary component of limestone and marble, and it crystallizes in many different forms. From tiny rhombohedral crystals to elaborate scalenohedra, called dogtooth spar, from flat transparent sheets to the strange property of double refraction, where a single crystal of clear calcite will produce two images of anything viewed through it, slightly offset from each other. This double refraction was noticed by the great 17th century physicist Christian Huygens, who used it to develop his wave theory of light. In Iceland, calcite, crystals called Iceland spar, were so well known for their optical properties that they became a subject of serious scientific investigations centuries ago. Aragonite is a polymorph of calcite, chemically identical, but with a different crystal structure. It is the form of calcium carbonate that corals and many other marine organisms build their skeletons from. Under the right conditions, aragonite can also form extraordinary crystals, delicate needles and prisms and radiating groups, sometimes in coral-like branching forms called phlosphae, or flowers of iron. There is something almost unbearably beautiful about the idea of these minerals, growing in the dark in the deep places of the earth, forming perfect geometric structures without any instruction or intention, guided only by the laws of chemistry and physics and the extraordinary patience of geological time. Among the richest sources of extraordinary crystals are pegmatites, a type of igneous rock that forms from the final stages of magma cooling, when the remaining melt is extremely enriched in water and rare elements. Pegmatites form when magma cools slowly deep underground, and the crystals that grow in them can become enormous. The feldspar crystals in some pegmatites are larger than a person. Tourmaline crystals can be over 1 meter long. Beryl, the mineral family that includes emerald and aquamarine, can form crystals of extraordinary size and clarity in pegmatites. The Etta mine in South Dakota, USA, contained spodumene crystals, a lithium-bearing mineral over 14 meters long. The Ural Mountains of Russia are famous for emerald-bearing pegmatites that have been mined since the time of the Russian Tsars. The gem-bearing pegmatites of Brazil, in the state of Minas Gerais, whose very name means general mines, produce tourmalines in a range of colors from deep green to vivid pink, aquamarines of extraordinary clarity, and topazes that rival diamonds in their brilliance. All of these crystals grew in the dark, in slow and patient silence, over millions of years. They had no idea they would eventually be found, cut, polished, and placed in rings and necklaces. They were simply being what chemistry required them to be, following the laws of atoms and molecules, building their perfect, patient geometries in the deep earth. Crystals do not only grow in rock, they grow in the sky. Every snowflake is a crystal of ice formed as water vapor freezes around a tiny nucleus of dust or pollen in the upper atmosphere. As the crystal falls slowly through the clouds, it passes through different regions of temperature and humidity, and each passage adds a new layer of ice in a slightly different pattern. The result, over the few minutes it takes for a snowflake to fall from cloud to ground, is a crystal of ice with a complexity and symmetry that seems almost impossibly delicate. The famous assertion that no two snowflakes are alike is, strictly speaking, a statement about probability rather than absolute certainty. But the number of possible arrangements of water molecules in a snowflake is so vast that even if snow fell continuously on every planet in the observable universe for billions of years, the chance of two identical snowflakes meeting would be almost zero. This is one of the most quietly astonishing facts in all of nature. The individual snowflake, that fragile hexagonal form falling slowly through the winter air, visible only for a moment before it melts on your sleeve, is, with almost perfect certainty, unique in the entire history of the universe. Every crystal is, in its own way, a statement about the beauty that emerges from order. From atoms arranging themselves according to very simple rules over very long times in the quiet, dark places of the earth, something of genuine and extraordinary beauty emerges. No planning, no intention, no design, just chemistry and time and patience. We have been traveling for a long time tonight, through rock and river, through mountain and glacier, through crystal and cave. And in every place we have visited, we have encountered the same quiet presence underlying everything: time. Not ordinary time, not the time of days and seasons and years, but deep time, geological time, a kind of time so vast that it reshapes our sense of everything else. This final section of our journey is perhaps the most important of all, because deep time is not just a fact about the age of the Earth. It is a perspective, a way of seeing the world that, once acquired, is permanently and quietly transforming. Let us take this slowly. The Earth formed approximately 4.54 billion years ago. This is a number so large that it defies easy imagination, and yet geologists and physicists have arrived at it through multiple independent lines of evidence: the radiometric dating of meteorites, the study of the oldest rocks and minerals on Earth, the modeling of stellar evolution, and the age of the solar system, that all converge on essentially the same answer: 4.54 billion years. Let us try to feel this number rather than merely understand it. If the Earth's entire history were compressed into a single year, if January 1st were the birth of the planet and December 31st were today, then the first month and a half of that year saw the formation of the solid crust, the gathering of the first oceans and the earliest stirrings of life. By March, simple single-celled organisms were living in those first oceans. They would remain the only life on Earth for an extraordinarily long time. It was not until November that complex, multicellular life appeared. The Cambrian explosion, that remarkable flowering of animal diversity that gave rise to most of the major body plans we recognize today, happened in the equivalent of mid-November, approximately 540 million years ago. Fish swam in what was, in this metaphor, late November. Land plants appeared in early December. The great coal forests of the Carboniferous period, which created the coal we still burn today, flourished in the second week of December. Dinosaurs arose around December 18th and dominated the land for the next 8 days of the metaphorical year until December 26th. The first primates appeared around December 28th. Our own genus, Homo, appeared in the last few hours of December 31st. All of recorded human history, every civilization, every war, every building, every book, every song, occupies roughly the last 12 seconds of the year. We are extraordinarily new here. Geologists have divided the history of the Earth into a hierarchy of time units, each one defined by changes in the rock record, particularly changes in the types of fossils found in the rock, which mark the rise and fall of different types of life. The largest divisions are called eons. There are 4: the Hadean, the Archean, the Proterozoic, and the Phanerozoic. The first 3 together, sometimes collectively called the Precambrian, cover the first 4 billion years of Earth's history, about 88% of all geological time. The Hadean Eon, named for the Greek underworld, is the earliest phase of Earth's history, approximately the first 500 million years. The surface of the Hadean Earth was alien, bombarded by meteorites covered in part by oceans of magma, lacking a protective ozone layer, its atmosphere thin and dominated by volcanic gases. And yet, tantalizingly, there is evidence that liquid water existed even in this early, violent period. And where there is liquid water, in the modern understanding, life is possible. The Archean Eon, from about 4 billion to 2.5 billion years ago, saw the establishment of the first stable continental crust and the emergence of life. The earliest fossils, stromatolites, layered structures built by communities of cyanobacteria, date to over 3.5 billion years ago. These communities of tiny organisms living on shallow seafloors were the dominant form of life on Earth for billions of years, and they slowly transformed the atmosphere by releasing oxygen as a byproduct of photosynthesis. The Great Oxygenation Event, approximately 2.5 billion years ago, was one of the most significant ecological transitions in the history of the planet, and yet it happened so slowly over hundreds of millions of years that it would have been impossible to perceive in any individual lifetime. The oxygen released by cyanobacteria slowly built up in the atmosphere, reacting first with the dissolved iron in the oceans and precipitating it out as iron oxide. The banded iron formations that are now mined around the world. Only when the iron was exhausted did oxygen begin to accumulate in the atmosphere. The oxygen that you breathe right now, the oxygen that fills your lungs with each slow breath in, was produced ultimately by photosynthesizing organisms that have been releasing it from the oceans and the land for over 3 billion years. You are breathing the accumulated work of 3 billion years of life. The Phanerozoic Eon, the one we currently live in, began approximately 540 million years ago with the Cambrian explosion, and it is this most recent 12% of geological time that contains the entire fossil record of complex animal life. The Phanerozoic is divided into 3 eras: the Paleozoic, the Mesozoic, and the Cenozoic. The Paleozoic, the age of ancient life, saw the development of most major animal body plans, the colonization of land by plants and animals, the rise of vast coal swamp forests, and ended with the largest mass extinction in the history of complex life. The Permian extinction, approximately 252 million years ago, in which more than 90% of all marine species and 70% of all land vertebrates went extinct. The cause of the Permian extinction is not definitively settled, but the leading hypothesis involves the eruption of the Siberian Traps, an enormous volcanic province in what is now Russia, over perhaps 1 million years. The volcanic activity released vast quantities of carbon dioxide and sulfur dioxide, warming and acidifying the oceans, destabilizing ecosystems that had taken hundreds of millions of years to develop. From this great dying, the Mesozoic era emerged, the age of reptiles, the age of dinosaurs. For nearly 180 million years, dinosaurs were the dominant large land animals of the planet, diversifying into an extraordinary range of sizes, shapes, and ecological roles. The sky was inhabited by pterosaurs, the oceans by plesiosaurs and ichthyosaurs, and ammonites, and extraordinary fish. And on land, the dinosaurs, from the EU largest animals to ever walk the earth to creatures no bigger than a cat, filled every available niche. And then, 66 million years ago, the Mesozoic ended. An asteroid approximately 10 kilometers across struck the Earth near what is now the Yucatan Peninsula of Mexico, releasing energy equivalent to billions of nuclear weapons, triggering a global winter that lasted for years as dust and soot blocked the sunlight. The non-avian dinosaurs were gone within a geological eye blink, a few thousand years. The ammonites vanished. Approximately 3/4 of all species on Earth went extinct, but the mammals survived. Small, warm-blooded, living underground or in burrows, eating insects and seeds. They made it through. The Cenozoic era, the age of mammals, the age we live in, began 66 million years ago in the aftermath of the asteroid impact and continues to the present day. In geological terms, it is the most recent chapter, and yet it spans a time almost 3 times as long as all of recorded human history, multiplied by 1 million. In the Cenozoic, the mammals that survived the end Cretaceous extinction diversified explosively, filling the ecological roles left vacant by the dinosaurs. Whales evolved from land-dwelling ancestors and returned to the sea. Horses evolved from small, dog-sized forest animals into the large, open plains runners we know today. Grass spread across the world, creating the vast savannas and prairies that changed the planet's ecology. The continents continued their slow drift. Antarctica reached its current position and became isolated enough from warmer ocean currents that it glaciated. The Himalayas rose, the Alps rose, the Andes rose. The closure of the Isthmus of Panama, the narrow land bridge connecting North and South America, about 3 million years ago redirected ocean currents in ways that influenced the onset of the current ice age. Our own lineage, the hominins, diverged from the lineage leading to chimpanzees approximately 6 to 7 million years ago in Africa. We walked upright, made tools, made fire, made art, made language. We are the most recent of a very long series of experiments in intelligence and social complexity that evolution has been conducting on this planet. And the planet itself, 4.5 billion years old, patient beyond all imagining, continues its slow work. Deep time does not end with the present. It continues forward into a future as vast and as patient as the past. Over the next 100 million years, the continents will continue their drift. The Atlantic Ocean will continue to widen. Africa will slowly collide with Europe, closing the Mediterranean Sea and raising a new mountain range. Australia will continue its northward journey and eventually collide with Southeast Asia. California will slowly slide northward along the San Andreas Fault, and in about 10 million years, what is now Los Angeles will be adjacent to what is now San Francisco. In about 250 million years, all the continents may again gather into a new supercontinent, which some geologists have already named Pangaea Proxima, continuing the cycle that has repeated perhaps 3 or 4 times in the past 2 billion years. In about 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, large enough to engulf the inner planets. The surface of the Earth will be seared to a temperature at which rock melts. The oceans will have long since evaporated. Whatever life remains on Earth, if any remain, will have had to have found a way to adapt to conditions growing progressively more extreme as the Sun slowly brightens over the next billion years. But for now, for this brief and beautiful moment in deep time, the Earth is precisely as it is. The oceans are the right temperature for liquid water. The atmosphere is breathable. The continents are in their current arrangement, producing the weather patterns and ecosystems we know. The glaciers are where they are, the rivers are carving their valleys, the crystals are growing in the dark. And we are here, aware enough to wonder about it, and grateful enough, on our best days, to feel the quiet astonishment of it all. There is something deeply soothing about sitting with the concept of deep time. It is not frightening as it might at first seem. This idea of human history as 12 seconds at the end of a vast geological year. It is, in its own way, profoundly comforting. The Earth does not need us to worry for it. It has been doing this, shaping and reshaping itself, raising mountains and eroding them, opening and closing oceans, experimenting with life forms beyond counting. For 4.5 billion years, it will continue to do so, with or without our understanding, for billions of years more. Our brief presence in this story is not insignificant just because it is brief. Every moment of geological time has been significant. The first cells, the first fish, the first footprint on land, the first flower, the first song. The brevity of our time does not diminish it. If anything, it makes it more precious. We are, as far as we know, the only beings in the history of this particular rocky planet who have looked up at the stars and wondered about their own origins. Who have looked down at the ground and understood that the stone beneath their feet is old beyond imagining. Who have held a fossil in their hands and felt the weight of deep time. This is something. In 4.5 billion years of history, this is something entirely new. A creature that knows it is standing on an ancient planet and is moved by that knowledge. There is an old geological saying, though it is really more of an observation than a saying, that the present is the key to the past. It means that by watching the world as it is today, watching rivers deposit their sediment and volcanoes build their cones and glaciers carve their valleys, we can understand what the features of ancient rock were telling us all along. But equally, and perhaps more poetically, the past is a key to the present. The landscape we inhabit today was shaped by processes that were complete long before any human walked through it. The valley was carved by a river long before the town was built in it. The hills were formed by ancient compression long before the roads wound around them. The stone of which the oldest buildings are made was itself built by processes that finished millions of years before the first human quarried it. Reading the rock record is one of the great quiet pleasures of a geological education. It is the ability to look at a cliff face, or a road cut, or a riverside exposure of bedrock, and to understand the story written there. not just intellectually, but with a kind of felt sense of what that place was once like, what it looked like when the rock was being laid down, who or what might have been living then. Stratigraphy is the branch of geology concerned with the study of rock layers, strata, and their interpretation. It is, in its essence, the reading of the Earth's autobiography. The fundamental principle of stratigraphy was articulated in the 17th century by a Danish scientist named Nicholas Steno, who observed something that seems obvious in retrospect, but was genuinely revolutionary at the time. In any undisturbed sequence of sedimentary rock, the oldest layers are at the bottom, and the youngest are at the top. This is called the principle of superposition, and it allows geologists to determine the relative ages of rock layers without needing to know their absolute ages in years. The layer below is older than the layer above. The fossil in the lower layer lived before the fossil in the upper layer. The environment recorded in the lower layer predates the environment recorded in the upper layer. It sounds simple, but when applied to the complex, folded, faulted, and tilted rock sequences found in real mountains and real cliffs, stratigraphy becomes a sophisticated art. The art of recognizing which layers were originally horizontal and which have been tilted by later movement, which sequences are complete and which have gaps, which unconformities, surfaces where layers are missing, represent periods of erosion or non-deposition that may span millions of years. An unconformity is one of the most haunting features in geology. It is a surface in the rock record that represents a gap in time, a period when sediment was not being laid down or when previously laid down rock was being eroded away. James Hutton, the 18th century Scottish geologist who is often called the father of modern geology, recognized a famous unconformity at Siccar Point on the Scottish coast in 1788, where steeply tilted ancient rocks are overlain by nearly horizontal younger rocks. Hutton understood what that boundary meant, that the lower rocks had been laid down as horizontal sediments, then buried, then heated and tilted and deformed, then slowly uplifted and eroded for millions of years, and then submerged again and covered by a new sequence of horizontal sediments. The boundary between the two sequences represented not just a change in rock type, but an enormous gap in time, what Hutton called an abyss of time. It was one of the moments that led him to the remarkable and then radical conclusion that the Earth was incomprehensibly ancient. Standing at Siccar Point today and looking at those layered rocks, the old grey Silurian greywackies tilted steeply on their end, the younger red Devonian sandstone lying nearly flat on top of them. You are looking at a gap of approximately 65 million years. 65 million years of geological time compressed into a single visible boundary in the rock. For much of geological history, geologists could only determine the relative ages of rocks. This layer is older than that one. This event came before that one, but not their actual age in years. The discovery of radioactivity in the late 19th century changed this completely. Radioactive elements decay at constant, predictable rates. Uranium slowly transforms into lead. Potassium decays into argon. Carbon-14, a radioactive isotope of carbon taken up by living organisms, decays back to nitrogen. Each of these transformations happens at a specific rate, expressed as a half-life, the time it takes for half of the radioactive atoms in a sample to decay into the stable product. By measuring the ratio of parent radioactive atoms to daughter stable atoms in a rock sample, geologists can calculate how long ago the rock formed. This is radiometric dating, and it has given geology the ability to assign actual ages, in millions or billions of years, to rocks and geological events across the entire history of the Earth. The results are, in their quiet way, Astonishing. A lump of granite that looks like any other lump of granite might turn out to be 300 million years old. An apparently unremarkable piece of gneiss might be 2.5 billion years old. And those tiny zircon crystals from the Jack Hills of Western Australia, barely visible to the naked eye, are 4.4 billion years old, older than almost anything else on Earth's surface. The rocks know when they formed. They carry their ages within them, quietly in the ratio of decaying atoms, waiting for us to learn how to ask. Using the rock record, geologists have been able to reconstruct the ancient geography of the Earth. Where the continents were, what the seas looked like, where mountains rose and where they have since eroded away. This field, called paleogeography, paints extraordinary portraits of worlds that no longer exist. 500 million years ago in the Cambrian period, much of what is now North America lay near the equator, covered by warm, shallow tropical seas. The great continent of Gondwana, a supercontinent made up of present-day South America, Africa, Antarctica, Australia, and the Indian subcontinent, occupied the southern part of the globe, including the South Pole. 300 million years ago, the equatorial regions of what is now Europe and North America were covered by vast, dense swamp forests. The Carboniferous coal forests, the source of most of the coal that powered the Industrial Revolution. These forests were warm and humid, filled with giant horsetails and scale trees reaching 30 meters tall, and populated by enormous insects that could reach such sizes because the atmosphere then contained significantly more oxygen than it does today. 150 million years ago, in the Jurassic period, the supercontinent of Pangaea was breaking up. The Central Atlantic was just opening. Dinosaurs roamed across landscapes we would find unfamiliar but not entirely alien. Forests of conifers and ferns and cycads, warm and mostly lacking the flowering plants that would later diversify so explosively in the Cretaceous period. Each of these ancient worlds can be reconstructed from the evidence in the rocks, from the types of sediment preserved, from the fossils found within them, from the orientation of ancient magnetic minerals that record the direction of the Earth's magnetic field at the time of formation, from the geochemistry of ancient soils and waters. The rocks remember everything. They simply require someone patient enough to read them. The Earth is not grey. The colour of the Earth goes deep into the rock itself, into the minerals that make up the stone, into the iron that stains sandstone red, and the copper that turns malachite green, and the manganese that colours amethyst purple. Minerals are the individual chemical compounds that make up rocks. More than 5,000 mineral species have been described, each one with its own crystal structure, its own chemical composition, its own distinctive physical properties, its own color and luster and hardness. The color of a mineral is often its most immediately striking property. And it is often the result of the presence of small amounts of particular elements or of defects in the crystal structure that affect how the mineral absorbs and reflects light. Iron is the fourth most abundant element in the Earth's crust, and it is responsible for some of the most vivid colors in the geological world. When iron oxidizes, reacts with oxygen, essentially rusting, it produces iron oxides, hematite, goethite, and limonite in shades ranging from deep brick red through ochre yellow to brown. The red deserts and red sandstones of the world, the red rock canyons of Utah and Arizona, the red soils of Australia's outback, the red cliffs of Devon in England, owe their color to these iron oxides. Even tiny amounts of iron oxide coating the surfaces of individual quartz grains can produce the vivid red and orange colors that make these landscapes so striking. Mars is red because of iron oxide. The same chemistry on a planetary scale giving that distant world its distinctive rusty color. When you look at the red deserts of Earth, you are seeing the same chemistry that colors an entire neighboring planet. Where iron produces reds and ochres, copper produces the most extraordinary greens and blues in the mineral world. Malachite, copper carbonate hydroxide, is a deep, vivid green, banded in concentric patterns of light and dark, formed in the oxidation zones above copper ore deposits. Azurite, a related copper mineral, is a deep and brilliant blue. The combination of the two, often found growing together, produces patterns of extraordinary natural beauty. Turquoise. The mineral that has been prized by human cultures from ancient Egypt to the pre-Columbian Americas owes its distinctive robin's egg blue to the Uffiuose. Presence of copper in its structure, modified by the presence of iron, which can shift the color toward greener tones. Copper mineralization in a rock face produces a landscape of extraordinary color. The ochre and brown of the iron oxides in the surrounding rock, the vivid green and blue of the copper minerals in the veins and pockets and cavities. Gemstones are minerals, or occasionally rocks, that are prized for their beauty, rarity, and durability. They form through the same processes that create all other minerals, but in conditions that produce exceptional clarity or color or crystal size. Diamonds form over 150 kilometers below the surface of the Earth, at temperatures over 1,000 degrees Celsius and pressures over 45 kilobars. They are made of carbon, the same element as graphite and coal and charcoal, but organized into a crystal structure of such rigidity and perfection that it is the hardest natural substance on Earth. Many of the oldest diamonds contain tiny inclusions, other minerals that were trapped inside the diamond crystal as it grew, that are themselves windows into the conditions of the deep Earth billions of years in the past. Diamonds are not just beautiful. They are geological messengers from the deep interior of the Earth, carrying within them samples of rock from conditions and depths that no drill has ever reached. Rubies and sapphires are both varieties of the mineral corundum, aluminium oxide, distinguished only by their trace elements. Rubies are red because of chromium. Sapphires are blue because of iron and titanium. The same mineral, subtly different chemistry, entirely different colors. All of these stones formed in the ordinary processes of geological history. They are the result of particular combinations of chemistry and temperature and pressure and time. But the patience required to create them, and the beauty of what that patience produces, is something that human beings have recognized and responded to in every culture and every era. The Earth makes beautiful things. It simply takes its time. The coast is one of the great meeting places of geology. Here, the processes of the land encounter the processes of the sea, and the result is a landscape of extraordinary dynamism and extraordinary beauty. Beach and cliff, and sea stack and cave, wave-cut platform and arch, estuary and salt marsh and tidal flat. Every coastline on Earth is the product of a unique combination of factors: the type of rock that underlies it, the energy of the waves that strike it, the tidal range, the supply of sediment from rivers, the direction of longshore drift, and the history of sea level change over geological time. Cliffs form where hard rock meets the sea and the waves erode it from below. The process is slow but relentless. Waves, especially in storms, hurl water against the base of the cliff with enormous force, exploiting every crack and weakness in the rock. They force air into cracks, and the compressed air shatters the rock when it expands again. They carry sand and pebbles that grind against the base of the cliff, undercutting it until the unsupported rock above collapses. But other coastlines build outward, rather than retreating. Where rivers bring large quantities of sediment to the coast, the sediment is deposited in deltas and beaches and offshore bars. Where coral reefs grow, they build carbonate platforms that may eventually emerge as limestone islands. The world's coasts are in a state of constant, slow change, retreating here, building there, shaped by the conversation between the energy of the sea and the resistance of the land. The coastline as we know it today is not the coastline that has always been there. Sea level has risen and fallen dramatically over geological time, responding to the comings and goings of ice ages, to the changing volume of the ocean basins as the seafloor spreads and subsides, to the gradual building and erosion of mountain ranges that store and release water. During the last glacial maximum, approximately 20,000 years ago, sea level was about 120 meters lower than it is today. The continental shelves were largely dry land. Britain was connected to France. The North Sea was a broad, grassy plain through which mammoths and woolly rhinoceroses roamed. As the ice melted over the following 10,000 years, sea level rose, drowning the continental shelves and reshaping the world's coastlines into something closer to their current form. Below the sea today, on the continental shelves, there are submerged river valleys, drowned beaches, ancient peat bogs and forests. Landscapes that were once dry land, now preserved in cold, dark, oxygen-poor water. The coast is always temporary. In geological time, every shoreline is merely the current position of a boundary that is always moving, always responding to forces that operate on scales far larger than any individual beach or cliff or sea stack. But within a human lifetime, the coast can feel eternal. The cliff you visited as a child is still there, slightly diminished when you return as an adult. The beach has shifted its shape but is still recognizably itself. The great permanence of the sea, the familiar sound of waves, the smell of salt and seaweed and wet stone. These feel ageless because they are, by any human measure, essentially unchanged. This is one of the great gifts of geology. It holds two truths simultaneously. Everything is changing, always, at every scale, and everything at the scale of a human life appears reassuringly, beautifully still. We have spent this evening traveling through the great landscapes and dramatic processes of geology, the Himalayas and the Grand Canyon, the glaciers of Scandinavia and the crystals of Mexico, the hot springs of Iceland and the coral reefs of the Devonian Sea. These are extraordinary places and extraordinary things. But geology is not only in the extraordinary, it is in the ordinary. It is in the path you walk to work. It is in the stone of the walls around you. It is in the gravel of a garden path and the clay of a pottery mug and the sand of a window glass. It is in the iron of a frying pan and the calcium of the milk in your morning coffee. Every material thing in the human world has a geological origin. Every metal, every ceramic, every building stone, every glass object, every piece of jewelry. Even the plastic in modern objects began as organic material, the compressed remains of organisms that lived millions of years ago, that was then chemically transformed by geological processes of heat and pressure over millions of years. We are surrounded at every moment by the products of geological time. We live inside geology as surely as we live inside the atmosphere. Walk through any old city and you are walking through a geological collection. The different stones used in buildings, in walls, in pavements and curbs and decorative facings represent a tour through different geological formations, different periods in the history of the Earth, different regions of the world. Portland stone, used in so many of London's great public buildings, St. Paul's Cathedral, the British Museum, is a Jurassic Oolitic limestone from the Isle of Portland in Dorset, formed approximately 155 million years ago in the shallow waters of a warm Jurassic Sea. If you look closely at a block of Portland stone, you can see the tiny spherical grains, ooids, that formed as calcium carbonate was deposited around small particles rolling in shallow, agitated water like a microscopic geological pearl. The grey granite of Aberdeen in Scotland, which gives that city its distinctive silvery appearance, is a Devonian intrusion, approximately 380 million years old, formed deep in the crust when Scotland was part of a mountain range comparable to the modern Himalayas. The crystals of quartz and feldspar and mica are large enough to see individually, evidence of the slow cooling that produced them in the depth of the crust. Every city is built on its local geology and built partly from it. The materials available in each region, limestone here, granite there, sandstone or slate somewhere else, have shaped the architecture of every culture in every era. The local stone is the visible expression of the geology beneath the city, the foundation of everything above it. Of all the geological features of the world, perhaps none has had a more direct and immediate effect on human history than soil. The distribution of fertile soils, the product of geology, climate, and biology working together over thousands of years, has shaped where civilizations arose, where they thrived, where they faltered. The great river civilizations of the ancient world, Mesopotamia between the Tigris and Euphrates, Egypt along the Nile, the Indus Valley civilization of what is now Pakistan, the Yellow River civilization of northern China, all arose in places where river flooding deposited rich, fine-grained sediment on broad floodplains. These soils, renewed annually by the river's overflow, were extraordinarily productive, and they supported the dense populations that made urban civilization possible. Soil is geology made biological. It is the meeting point of the mineral world and the living world, the interface where rock becomes food, where the slow time of geology is converted into the quick time of life. When you eat anything really, from a piece of fruit to a piece of meat to a grain of rice, you are eating, in an ultimate sense, geology. The minerals in your food were once rock. The carbon in every organic molecule was once carbon dioxide in the atmosphere, or carbonate in the sea, or coal in the ground. The iron that carries oxygen in your blood was forged in the interior of a star that died before the Earth was born, incorporated into the Earth at its formation, cycled through rock and ocean and soil and life, and is now part of you. We are, all of us, made of ancient geology, made of star stuff and rock, shaped by 4.5 billion years of planetary history, briefly and beautifully alive on the surface of this patient, extraordinary world. We have traveled a long way tonight. We have walked through the deep time of the Earth, from the hot chaos of its formation to the quiet, living present. We have felt the patience of rock forming over millions of years, the slow rising of mountains driven by the invisible movement of plates, the gentle, continuous sculpture of water on stone. We have descended through the layers beneath our feet, the living soil, the quiet aquifers, the crystal-lined caves, and found there a world as rich and varied as anything visible above. We have learned that ancient oceans are preserved in limestone, that sand carries within each grain the memory of a mountain and a river's long journey, that glaciers have carved the most beautiful valleys on Earth with nothing more than the patient weight of ice. We have found crystals growing in darkness over millions of years and understood that every snowflake is a unique and perfect crystal, here for only a moment before returning to the water cycle. And we have sat for a few quiet moments with the concept of deep time. that vast, patient, unhurried span of geological history that puts our own lives in their proper perspective without diminishing them. Geology teaches patience. It teaches perspective. It teaches us that change is always happening, but that the timescales of the Earth are so much larger than our own that from our position within them, most things appear beautifully, reassuringly still. The mountains are not going anywhere tonight. The rivers will still be carving their valleys tomorrow. The crystals in the dark will still be growing, adding their invisible layers, following the quiet laws of chemistry that have been in operation since before the Earth existed. The Earth is patient. And tonight, in the warmth and quiet of wherever you are, perhaps we can borrow a little of that patience for ourselves. Let your breathing slow to the rhythm of something ancient. Let the weight of your body settle into the ground as if you, too, were slowly becoming part of it. The Earth is 4.5 billion years old, and it has never once been in a hurry. There is nothing you need to do tonight that the mountains have not been quietly waiting to outlast. So rest now. The rocks will still be here in the morning. The rivers will still be carving. The crystals will still be growing. And you will still be here, brief and beautiful and made of the same ancient atoms as everything else. Waking slowly into another day on this patient, extraordinary planet. This has been Quiet Knowledge. Sleep well.